Hello, Mr. Betts here. Let's take a look at another optimization problem. This one is more of an analytical one, so we're looking at things going on in a coordinate plane. And the problem here, what we're looking for is a point along this parabola that is the closest to this point. So if we pick a point along here somewhere, we can find that distance between the two, and we want to figure out when is that distance going to be the smallest, and we want to figure out what are the x and y coordinates of that point. So what I'm going to do to start with for setting up my model is I'm just going to pick an arbitrary point, and I'm just going to call it x comma y. Remember, the coordinates of this point are 0, 2. And so to set up my function, I want to know what is the distance between these two. And so I'm going to set up an equation using the distance formula. So the distance formula, you could use Pythagorean theorem, or I'm just going to use the distance formula directly. So it's going to be the difference in the x coordinates. So that's just x squared. So difference in x coordinates is just x, and then we square it, plus the difference in the y coordinates, y minus 2, and square that. So this equation right here gives us the distance, which is what we're trying to minimize. So closest means the smallest distance. And we're going to have to do the calculus on this, but notice we have two different variables here. So what we need to do is eliminate one of the variables, and we are actually given the equation in the problem that's going to allow us to do that. So we're going to replace the y with 4 minus x squared. Another way to think about this is that we could write this ordered pair right here as x comma 4 minus x squared. So our distance is going to equal the square root of x squared plus 4 minus x squared minus 2 quantity squared. And just doing some cleaning up here, and I'm going to rewrite this in a form that's going to be a little easier for taking the derivative, because that's going to be our next step. We're going to have x to the fourth minus 3x squared plus 4, and then to the 1/2 power. So it's the square root of all that. I wrote it to the 1/2 power so that we can use the power rule on it. And so I just got this expression by expanding this and then combining like terms. Actually, I simplified the inside first, then I expanded it, and then I combined like terms. So now that we've done that, we want to figure out, I made a mistake here. I skipped a step. Back in the first step, I want to not only declare my variables, which were done for me, we have x and y, but I want to look at what the restrictions on x and y are going to be. Since we're looking in just the first quadrant, the x values are going to be in the range from 0 to 2. I know x equals 0 and x equals 2 are not actually going to be in there, but I'll include those endpoints. It technically wouldn't be in the first quadrant if x is 0 or x is 2. But we just won't include that if that does end up being our answer. The y values are going to go from 0 to 4. And so now let's go back and figure out on the range, on the domain 0 to 2, where are we going to have critical values on this distance function. So we're going to take the derivative. I'll just call it d prime. This is also dd dx. And that's going to be, so it's going to be 1/2. I'm going to put the 2 in the denominator for the 1/2. And then it's going to be this expression to the negative 1/2 power. So the square root's going to be in the denominator. And then with the chain rule, we have to multiply by the derivative of the inner function, which is going to go on top. So that's going to be 4x cubed minus 6x. And so now what I want to do is figure out where this derivative is either equal to 0 or is undefined. So I'm going to set it equal to 0. I do want to point out that the derivative would be undefined if the denominator is 0. X to the fourth minus 3x squared plus 4 is never going to be either 0 or negative, so we don't have to worry about that. What we do need to worry about, and where we are going to get critical value, is where the numerator is going to equal 0. So if the whole thing is equal to 0, that means that the numerator equals 0. So I'm solving this equation here. I'll do that. I'll solve it by factoring. So we can factor out a 2x, and then what's left is x squared minus 3. And I can factor that x squared minus 3 as a difference of squares. This is maybe not the best way to solve it, but it works. You could also solve this by just getting x by itself. So you get x squared equals 3 halves, and then square root of that. So we get critical values at x equals 0, x equals positive square root of 3 over 2, and x equals negative square root of 3 over 2. We're already going to include 0 as a critical value because we called that an endpoint, even though I mentioned that it's not technically in the interval. In fact, I should probably get rid of that. Let's just make it an open interval. Let's do things the right way. So 0 is not an option. Negative square root of 3 over 2 is not an option, so we can eliminate those. And our only critical value is going to be at the square root of 3 over 2. Now, I don't want to just assume that's going to be our minimum distance, because it's possible that's going to be a maximum distance, and the minimum would be at the endpoints, one or the other. And so I want to make sure that I verify with calculus that that's where it's going to be. So let's look at a sign chart. Since this is an open interval, we can't really use the candidates test. So we're going from 0 to 4, and square root of 3 over 2 is going to be somewhere in the middle. Sorry, we're going to 2, not 4. I do want to point out that 3 halves is bigger than 1. So when we take the square root of that, it's also going to be bigger than 1. So 1 is going to be on the left side. So if we plug 1 in to the derivative here, so a number between 0 and the square root of 3 halves, if we plug 1 in, we're going to get a negative number. So we get on top 4 minus 6, which is negative 2. On the bottom, square root's always positive, so it's going to be a negative. If we plug in a number bigger than the square root of 3 halves, we're going to get a positive. So this sign chart here tells us that the distance is decreasing as x goes from 0 to square root of 3 halves, and then the distance is increasing as the x coordinate goes from square root of 3 halves to 2. So we are going to have a minimum distance at that point. I want to make sure that I answer the question. So the question says, what are the coordinates? So I need an x and a y. So I'm going to write this as square root of 3 halves, comma, plugging that in here, we're going to have 4 minus 3 halves, or 8 halves minus 3 halves is 5 halves. And that's the coordinates. So if we plot the point at square root of 3 halves, comma 5 halves, which is going to be somewhere around here, that's going to be the closest that a point gets on this parabola to that point. I also want to justify this with calculus. So I'm going to say the distance. So I've been justifying a variety of ways just to see there's different ways we can explain this. So I'm going to say the distance is decreasing. So in the last example I did, I talked about the sign of the derivative. Now I'm saying that the value itself is decreasing, and that's because the derivative is negative. To the left of x equals square root of 3 halves, and the distance is increasing to the right. Okay, so since the distance is always decreasing to the left and always increasing to the right, it's going to be at an absolute minimum at x equals square root of 3 halves.